Well, welcome everyone to yet another lockdown and another lockdown stream. So thank goodness we been continuously doing this. So hopefully it should all work out pretty well. So this evening we're going to start off as we do with our normal meetings. Josh will be kicking off with the news, and then Chris will be taking over. Chatting to us about Red Dwarfs, which is one of my favourites. So it's going to be a good one. So just a reminder, at this point, no physical meetings, obviously because of level 3. As soon as we go to level 2, we will make a decision then as to what happens, as we did last time. Of course, it's just to keep us safe and to keep you safe as well. So there we go. So I'm going to hand over to Josh, and he's going to take it away with the news.
Great. Thanks, James. Hi, everyone. And yeah, thanks for tuning in for another of our virtual meetings. I'll just be looking at some interesting things that have been happening recently in astronomy and space-related news. Then I'll hand over to Chris for the main presentation. So let me just share my presentation here. Cool, and that should be coming up. Okay, so astronomy news, what's been happening above us? So in news, NASA Perseverance is now on its way to Mars. So if you'll remember James's last talk a couple of weeks ago, he spoke about the NASA Perseverance rover, which is on its way to Mars, and some of the really cool things that that's planning to do once it gets there. So the Perseverance rover, the vehicle that carries the rover through space, which is what we can see here, this is an artist's impression, but recently this has performed its first trajectory correction maneuver successfully. So as it goes on its course to Mars, it's scheduled to make a few of these maneuvers just to make sure it's still on course, that it's going to get there okay. And the first one was a success, so that's a big positive. Also, they've powered up the Ingenuity helicopter for the first time. So if you remember James's talk, this is the helicopter that it's sort of bundled underneath the rover. The idea is that once they get to Mars, this will launch and they'll sort of fly it around to see whether helicopter-type flights actually work on Mars. So just a few days ago, they powered this up for the first time. It hasn't been flying around, it's still traveling through space, but still this was the first time that they switched it on remotely to make sure it all works. All the battery levels were looking good, so that's a good sign. And yeah, everything's on track for a Mars landing in February 2021. So it'll be an interesting time next year because very close to that time will also be when the UAE's HOPE mission will be arriving to Mars, which is the HOPE orbiter, as well as China's Tianwen-1 mission that will also be landing around the same time. So watch Mars next year. And here's some more details about the recent, what was TCM again? Trajectory correction maneuver. So if I use my mouse here, you can see this is where we were at launch time, and this is where Mars was. And so what's happened recently is it's completed its first trajectory correction maneuver, just to sort of make sure that it's going to head in this way. There are other ones that are planned for the duration of its mission. And then eventually, once we're all over here, Mars is going to be here and it's going to land. So this is scheduled to be February next year. Also in the news, more about Betelgeuse's mysterious dimming. So now the latest thinking is this may have been caused by a stellar eruption from Betelgeuse itself. So if you've been paying attention to some of our talks over the past 6 months, you recall that the Betelgeuse, which is a star in the Orion constellation, it began dimming late last year, and we were really confused as to what was going on. Over the course of a few months, it lost 2/3 of its brightness, and a lot of people were speculating whether we were about to witness the end of Betelgeuse. It was going to go supernova, which would have been a pretty awesome sight. But now it's returned back to normal. And we're still a bit unsure Like, we can't say with 100% confidence what caused it. But the latest theory is that the star itself ejected plasma, which cooled to form a giant dust cloud. So similar to the way our sun has solar flares, occasionally material gets ejected into space, the idea is that Betelgeuse ejected a big bunch of this material, which, when it got far enough away from the star, from the sun, it cooled enough and then turned into sort of dark dust cloud. And so this is based on observations from the Hubble telescope, looking at things over a 3-month period where we've seen that there was an outburst of material. So if we look ahead to this, this is an artist's impression as to what we think may have happened. So we can see the star itself ejecting some plasma. It's getting shot out. And in this particular frame here, the idea is that this is being shot towards Earth. So when we look at the view here, sorry, I'll move that out of the way. So the idea is that when we see it from Earth, what we are seeing now is the cooled cloud of dust, or at least that's what we were seeing when it was dimming. Now it's back to normal, so this may have all gone. But that's our sort of latest thinking as to what happened with Betelgeuse, what caused that dimming. In other news, violent thunderstorms on Jupiter may form mushballs that fall from the sky. So this is some new observations that have come from NASA's Juno spacecraft, which is observing Jupiter. And it's looking at some of the interesting weather that we can see on other planets, especially a planet like Jupiter, which is a gas giant, very different to the rocky planets. So we've observed that there are clouds which are a mixture of ammonia and water. And due to the sort of updrafts and the currents, this can cause shallow lightning. And then ammonia-rich hail, which is called mushballs. So imagine hail, but instead of being solid like ice, it's sort of mushy. It's halfway between water and ice. And the thinking is that every so often that happens and dumps a load of ammonia sort of further down into the planet. And so one of the reasons this is interesting is because over time, Juno has observed that there are occasionally drops in the ammonia level. When it's looking at Jupiter's surface, it'll measure readings of how much ammonia is there, but then when they check again, it'll just be gone in that patch. And they haven't really been able to explain where is that going. So the new thinking is that with this bizarre space weather, maybe what's happening is that ammonia that's close to the sort of outer layer of Jupiter, maybe that is forming these mushballs and falling down where we can no longer observe it. So that could explain some of these weird readings in the levels of ammonia. Duckweed could be an important part of future astronauts' diet. So I found this one interesting reading about this because I'd never heard of duckweed. And if you've never heard of duckweed either, that's fine. But apparently duckweed, it's one of the fastest growing plants on Earth. It's the most protein-dense plant on planet Earth. In some parts of Asia, it's eaten as food, but in most parts of the world, we consider it a pest. It's a floating plant that grows on ponds. But one of the interesting things about it is it contains micronutrients that can help fight inflammation and radiation damage. And both of these things are things that we need to worry about when it comes to astronauts. We know that when people are in space, they are more exposed to solar radiation and things that can cause harmful damage over time. And when we think about big picture, long-term things like the idea of maybe one day colonizing Mars or something like that, all of these things involve long space flights. And the question is, how can we still feed our astronauts on those flights? So NASA has funded this new research into duckweed to look at this plant that grows here on Earth to find, can we grow this under different conditions? And so far the results are quite promising. We've proven that we can grow duckweed with limited light and limited area, which means that we might be able to grow this on board a spaceship. And given that it's such a good source of micronutrients that can help battle some of the afflictions that astronauts might face, The thinking is that in future, a duckweed salad could be a staple for future space explorers. So watch this space. Also in the news, mysterious fast radio burst has been detected earlier this year, closer to Earth than ever before. So you'll recall that in some of our past talks, James has mentioned fast radio bursts. So fast radio bursts, or FRBs, were first detected in 2007. Since that time, we've seen hundreds of them, and we're not quite sure what causes them. They're unexplained bursts of radio waves that they only last for a few milliseconds, but during that brief period, it has a massive amount of power and energy. And all of the FRBs that we've ever seen or heard have basically originated from outside our galaxy. However, new research shows that an FRB that we detected earlier this year, in April 2020, actually originated from within our galaxy. And the current thinking is that this came from a magnetar. You might remember magnetars from some of Chris's talks. A magnetar is a neutron star with a very strong magnetic field. And so this particular one is interesting because it's the closest that we've had an FRB to Earth. And this new research says that it's possible that some of the other FRBs that we've discovered over time, maybe these were also from magnetars. So we still don't know 100% for sure, but this is the new thinking with FRBs. And finally in the news, the US Pentagon has created a new task force to study UFOs. So the official mission is to detect and analyze unidentified aerial phenomena, or UAPs, that could pose a threat to US national security. So these days, in terms of Pentagon and the military, they generally don't like the term UFOs. Generally, they'll say UAPs, unidentified aerial phenomena. And this might sound quite wacky, but I was doing some reading into this, and one of the, I guess, more sensible explanations as to why they've done this is because they want to examine whether the UAP detections are actually just instrument failures. There have been some interesting videos, from the past few decades of US military planes encountering unexplained things, lights and things like that, but we're still not quite sure what they are. Are they UAPs, or is it just a fault in the instruments? So one of the things this new task force wants to do is actually look at these in a bit more detail to determine, hey, is there actually a problem with our instruments? Or is what we're seeing maybe some sort of classified military thing from a different country that they don't want us to know about, or those sorts of things? So there are some interesting things that this will be looking at that aren't necessarily related to the realm of aliens and little green men. So all in all, this new task force, even though it sounds exciting, it may not be as exciting as we hope. But we'll wait and see what happens. So that's all for the astronomy news for tonight. So now I'll pass us over to Chris for our main talk for the evening. I'll just stop sharing here. Thank you. Over to you, Chris.
Yep, thank you, Josh.
Actually, just before we begin there, Chris.
Yep.
Just for our viewers out there, you can't see me. I'm just the voice in the machine at the moment. Yeah, if you want to engage with us, ask questions, you can do so in the live chat, which should be, I think it's on the right of where you're looking usually. So say hello there on the live chat, and any questions you've got for Chris over the course of his talk, please pop them in there and then I'll relay them across in here. So all over to you, Chris.
Okay, thanks, James. Let's see how I go with sharing this. Get my PowerPoint up. Are you guys all good there? Can you see that? Okay. Yep, good. We're okay. We're underway. So hi, guys. Welcome. Tonight's talk is entitled Living Under a Red Dwarf Star. Favorable for life or not? In other words, the planets that are going around these stars called red dwarf stars, which we'll talk about, are the conditions on those planets suitable for life to get started and stabilize and evolve and so on, or not? That's the question which we'll delve into tonight, and then you can make up your own mind at the end of the program. A few little housekeeping points. As James said, questions can be in the chat area, and they'll be addressed at the end of the talk. 3 points there. One is the questions must not be too hard. Secondly is we must have a lot of fun tonight. So we will. We're going to have a lot of fun. We're going to take things slowly and, enjoy ourselves. Also, I have a handout. Let's get that up in front of the camera thingy there. We have a handout that I've done about what I talked about tonight. And this will be available at our next physical meeting. Hopefully that'll be sooner rather than later. So, but anyway, that's a little bit of bait for you to come to the first physical meeting that we have, and obviously we'll announce that. I also want to use this topic because it's lent itself perfectly to discuss a lot of astronomical principles associated with the topic. So I'm going to adopt that strategy. So we're going to talk about principles in general and then apply them to red dwarf stars and their planets as we move forward. So let's do that. So the next question is, why do a talk on this topic, on red dwarfs and the planets around them? Well, it's just over recent years, you've probably noticed that the media have been doing a lot of exposure and talking about these exoplanets that have been discovered with the new fancy telescopes, and that these planets they're talking about have got liquid surface water, which we know, of course, is pretty much essential for life to get started and then evolve and continue on with. In star systems that they've talked about in particular, the TRAPPIST-1, the LHS 1140 system, and of course, a lot of excitement, Proxima Centauri. Hello, that's our closest star system to us. And that has got exoplanets that could have liquid surface water. Yay. So what have all these star systems they're talking about got in common? The bottom line is that they are all red dwarf stars. And that's what we're going to talk about tonight. While we have a lot of fun talking about cats. So let's talk about red dwarf stars and exoplanets. Like, could they have cats on these planets? And could the cats evolve? You wouldn't want to be on one of these planets, would you? You'd need more than factor 50, I think, if you're sunbathing there. But let's move ahead. Okay, so there's 3 key messages I want to impart on red dwarf stars. Firstly, they are abundant. They are the most abundant type of stars in our galaxy. They make up 70% of the stars in our galaxies are red dwarfs. They are long-lived. They live extremely long, stable lives. You're going to find out why. They're very hyperactive, not the Ritalin type of hyperactive, but their surface has got a lot of magnetic activity going on top of it. We'll discuss that further. But really what I want to say is it's got that going on, and that causes what we call frequent super flares, which you're going to learn about. And that's really, really relevant. So just remember, red dwarf stars, there's 70% of all the stars in the galaxies. Actually, you don't actually see them with your naked eye. They're too small. You've got to see them with your telescope. They live long, stable lives, and they have a lot of sort of like, you know how we talk about solar flares? They're called super flares, really powerful solar flares and much more frequent. As for the conditions on the planets that are going around these dwarf stars, a lot more complicated. As you're going to find out, it's not straightforward. It is very complicated. So we're going to work our way slowly through that using first principles. These are the principles that I'm going to do in this order. We're going to talk about stellar spectral classes. How do you classify stars? We're going to talk about stellar evolutions, briefly how stars evolve. We're going to talk about the initial mass function, often abbreviated to IMF, and that refers to the spread of the numbers of stars according to their size. We'll talk about the internal stellar heat transfer. In other words, how does that real huge temperatures at the core of these stars, where nuclear fusion is occurring, how does that heat work its way up from the core through the star and then leaves the surface of the star? That's really relevant. So we'll talk a little bit about that. We're going to talk about the concept of flare stars, which are relevant for red dwarfs. We will talk about the main methods they use for finding these exoplanets that the media are telling us all about and getting us all excited. Well, I'm excited anyway, that's enough. And we're going to talk about the potential properties. What are the conditions like on these planets that are orbiting red dwarf stars? So let's rock and roll, guys. Let's do it. So first of all, stellar spectral classes. The key message is going to be here, red dwarf stars are really cool. Not as in fancy sunglasses, Ray-Ban cool, but as in low temperature cool. Okay, so spectral classes are based on the surface temperatures of the stars. And going from big stars to small stars, they're called O, B, A, F, G, K, M. Now, I know what you're probably thinking. You're probably thinking to yourself, is he got too many cats perhaps up there? What's quite wrong? When I went to school, the alphabet went something like A, B, C, D, F, G, and so on. So what are all these numbers about? Well, it's all for historical reasons. Stars were originally classified according to the strength of their hydrogen spectra. In other words, how much hydrogen could be identified in their atmospheres from spectral analysis. And then as they got a better understanding of stars, they then realized, hey, it actually makes more sense to classify stars according to their surface temperature. But they'd already made these classifications, so they ran with them. So the order goes O, B, A, F, G, K, M. And you think, how am I going to remember that? Well, for all you ladies out there, it's called Oh, be a fine guy, kiss me. Or all you guys out there, Oh, be a fine girl, kiss me. And there are also another subgroup of dwarfs, of stars called L and T. And I usually do things like this, for example, you could add to it. But anyway, those are your main classifications of stars. You'll see here, there on the right, here are your red dwarfs. You might say, well, where do red dwarfs fit in? They are the K, the K and the M class spectral classes. This here is your red dwarfs, these two spectral classes here. And as you're going to find out shortly, these classifications, according to their surface temperature, also reflects from that how large or massive a star is and its life expectancy. So let's move on. I put this graph here, or this table rather, just to compare and contrast where does our sun sit with the really hot stars and what they're like, and the really cool stars, namely the red dwarfs, the K and Ms, and what are the conditions like on those. So our star, the sun, is a G class. And you'll see the surface temperature here in the G class is raised from 5,500 to 6,000 degrees. The surface of our sun is about 5,800 degrees. And you'll see from here the way they've done it. You've got your mass here, because it's one for our star, one solar mass, the mass of our sun. That refers to its size. As you can see where it fits in here, our sun fits bang on one. L stands for luminosity, or the brightness, how bright it is compared with our sun. And our sun, of course, is in this G class, and it happens to be, naturally one solar luminosity, or the brightness of one sun. Also of relevance here is how long one of these stars lives on the main sequence. You'll find out shortly the main sequence is where stars spend 90% of their time, where they're sitting burning hydrogen to helium in their core, and that represents the most stable part of their life. And our sun, the G class here, can be anywhere from 8 to 15 billion years they spend on that stable main sequence. Our star, the sun, is about 10 billion years. And just in case you're wondering, we're about halfway through that. We're about 5 billion years into that 10 billion years of a relatively stable state on the main sequence. Now let's move up here into these more hotter stars. Here's your O and B. So let's look at the O's. Look at these guys. They can be over 33,000 degrees. Ouch. That's hot. Look at the size of them. They can go up to 60 times the mass or the size of our sun. Look how bright they are, luminosities. They can go up to 800,000 times brighter than our sun. You'll need a bit more than a pair of Ray-Ban sunglasses to stop that glare, I'm sure. Hey, but look at this interesting thing. Look at their life expectancy on the stable main sequence. You're only dealing with 1 to 10 million years, not as opposed to 10 billion years for our sun. Why is that so? You're probably saying it all comes down to the fact they are large. They have such huge masses, and it's mass that drives gravity, the gravitational inward force, which raises the temperature in the core of that star, which in turn dictates the rate at which it burns up, causes nuclear fusion of hydrogen to helium. You've got a big star, 60 times our solar masses, got much more gravity. The temperature and the pressure in that core is going to be much, much larger. It's going to race through that hydrogen much, much quicker. So these large, hot stars like the O and Bs have really short, stable lifespans. That's really important, because why isn't put, hey, let's go down the other end of the spectrum to the K and M classes here, where our red dwarfs sit. Notice how cooler they are. You know, you're looking down to about sort of, 3,000 odd degrees as opposed to 5,800 for our sun. You'll see here the very low mass, so the very small and the very cool. So you're getting down to what, about 8% of the size of our sun. So these guys are really low mass, they're really small, they're really cool, and look how little brightness they've got, how dim they are. You're getting down to less than 1% the brightness or dimness of our sun. So the small, the cool, and the really dim. But here, look at this. This is interesting. Their life expectancy, sitting on this main sequence in this most stable state, 56 billion years they can stay in that state. The age of our universe is what, 13.8 billion years? In other words, these stars are going to be around for much longer than our universe has ever existed to this date. So you're starting to see these cool, small, dim red dwarfs lead long, long lives because they've got low mass, so low gravitational force, which means the temperature and the pressures aren't so great at the core, so they burn hydrogen really, really slowly. A little bit off track, but another little interesting point here is the nature, how they're structured, their internal structure. Rather than just having a solid core burning away hydrogen, they actually mix, as I'm about to show you in about 10, 15 minutes time, they mix their contents up. So the hydrogen is constantly getting all churned and mixed up there. So not only have they got a long time with low pressures to burn stuff away, the core region is constantly being replenished with new hydrogen from the outer layers. And you'll get to see that shortly. So yeah, hope you've seen that the red dwarfs are small, dim, and they're really stable. Now, what have we got here? Let's move on to the next topic. Stellar evolution. And as we talked about, red dwarfs are stable for a long time. So we're going to move on. And this is the Hirschsprung-Russell diagram. You'll never get a talk of mine and escape this diagram. Single most important diagram in astronomy. And I refuse to apologize for putting it on again. I absolutely refuse. It's such an important diagram, Hirschsprung-Russell diagram. And this is how it goes. Along the x-axis, you've got your spectral classes, O, B, A, F, G, K, M. You all know what that means now. It reflects the size of the stars, the luminosity of the stars, and it reflects their surface temperatures. You can see, and it's logarithmic, 3,000 right up to 30,000 plus over here. Up the y-axis, you've got the brightness or luminosity. And if you get a cluster of stars, say an open cluster or globular cluster, and you plot the temperature or the spectral class of the star against its luminosity or brightness, you'll get most of the stars, 90% of them, you'll see this nice big strip up here. And that's your main sequence. That's the most stable state where stars spend 90% of their time burning hydrogen into helium at their cores. And look what you got down here. Here's your red dwarfs. They all live down here. These babies up here, the big OBs, they burn themselves out in a few million years. Our sun sits about, just trying to find our sun in here. There it is. There's our sun that's going to live for about 10 billion years total. These guys down here are going to live for 56 billion years in that nice stable state. So why am I rabbiting on like this about this whole concept is this bottom line here. It makes sense. The best time for a planet to harbor life, to get life get started, life to be sustained, life to evolve, for human beings to evolve into cats, because I think cats are a lot brighter than us some days, then you want a star, you want to go around a star that's in a stable main sequence stage for as long as it possibly can. So it follows where my logic is all leading to. These red dwarf stars are looking pretty good candidates to host planets for long lengths of time and allow time for life to get started and do its thing. Like, have some golden arches, McDonald's, proper civilization. Okay, the next thing, initial mass function. And you're about to see here, red dwarfs are very, very common stars. I've already alluded to that at the start. And here's the nice little pie diagram illustrating to what I told you early on, that red dwarf stars, which is all this red and orange color here, they make up 70% of the stars in the Milky Way galaxy. And you'll notice the bigger the stars get, the less and less there are of them. And it's actually exponential. If you had a nice pyramid with your large stars at the top, and then you spread it out with your base, with all your small stars, it's actually exponentially more and more star numbers, the smaller the stars you're counting. It's quite a whole thing in itself. We can do a talk on that one day on star formation. But anyway, you get the gist. So these stars out there, and remember the other thing I told you, because you're probably looking out the window now, it's probably a bit cloudy out here, but anyway, you're probably thinking, well, let's go outside, let's see some of these stars. You won't see them because they're so small and so dim, you need a high-powered telescope to see them. They're out there, we don't see them with our eyes, naked eyes, but they're out there and they're making up 70% of the stars. You can go tell your flatmates that if you like. Okay, now internal stellar heat transfer. So how do stars get rid of the energy, that heat and energy that's all created by nuclear fusion in the core, and it works its way up to the surface? And you don't just go, it works its way out of the surface. No. It's really relevant the models of what goes on and how the heat is transferred. In particular, you're about to see that red dwarfs, it's totally by the process of convection. Let me explain. Okay, now here's the three forms of heat transfer. And as you're probably aware, heat always goes from hot to cold. That's one of the basic thermal laws. And you'll see here's a nice everyday example, and it's got, you're cooking your dinner at night, and it's got this, all three processes are going on. You've got your flames here of your fire. They're emitting hot photons, which are traveling through that short space, that's traveling through here between the short space and the pan, and that's radiation. High energy photons being transferred. They hit the bottom of the pan, and then by conduction, little molecules heat up that make up the pan. They all heat up, and then they transfer that heat or kinetic energy to the next one, and so on and so on. And that's called conduction. And slowly the inner parts of the bottom and then the inner parts for the inside of the pan heats up, and eventually if you hang on to the handle enough, you'll get a sore hand, because obviously that's heating up too, and that's conduction. And then if you lift up the pan lid, you'll see the water boiling away. And what's going on in here is the process called convection. And that's where that heat from the inner pan that got there through radiation and then conduction, that is heating up the little particle molecules of water, which then heat up, start moving faster and faster and faster. And as they get hotter and hotter, they start rising, little cells or packets, if you will. They start rising up like that to the surface of the pan. They hit the surface, they dissipate the heat outwards, so they naturally lose the heat. They cool down, and then they fall back down again, and the cycle repeats. And depending on what sort of fluids and temperatures you talk, it's all with equation stuff. You can actually work out the size of the individual little cells. But the point is that cells heating up, little cells of energy, they rise, dissipate their heat, and sink back down again. And that occurs in little packets of cells. And that's an important, particularly as you're about to find out in stars, a way you dissipate heat out to the surface of something, whether it be the surface of hot water or stars. So here's a model which is a very successful model, so almost certainly is so, how heat escapes a star of one solar mass, namely our sun. So you've got your core here where your temperature is about 15 million degrees and hydrogen's quite happily fusing into helium, and it's liberating energy in that process. It's hot enough at the outer parts of that core for the energy to be dissipated by radiation, where it's just high energy photons are working their way through all the plasma and so on, just zigzagging backwards and forwards, slowly losing energy. But that the inner 2/3 of the inner part of the sun, it's called the radiative zone, and its radiation is the main process at which the heat is escaping, heading towards the cooler surface of the star. About the outer third or so, that's where it starts cooling down and you start getting convection starting to kick in. And you get little cells here of plasma, they heat up and they start rising up in little cells or packets, dissipate their heat and sink back down again to the outer part of the radiative zone. So naturally that's called the convection zone. And that's almost certainly what's going on in our sun, how it's getting rid of the heat it's generating. So let's now have a look at what's going on in a red dwarf. The model suggests what's going on because the temperatures are so much cooler. It's not hot enough to have a radiative zone. So the whole context of the star is just all convection. It's just one big convection process. So you've got your hydrogen fusing into helium here, and you get these hot cells, they're rising up like that, dissipating, coming down. Now, there's two things that come out of that. One is, because I mentioned you've got all this tuning going on inside, you haven't got a dedicated core, just hydrogen turning to helium that one day is going to run out of hydrogen. You've got this constant tuning, so there's constant replenishment in these central core regions, ongoing replenishment of hydrogen. So you've got this mixing going on. So that adds to the whole factor that these guys can live so much longer. The hydrogen burning rate is lower because less energy, because less mass, less gravity driving it all, but you've got this tuning effect. But more relevant to this talk is the second consequence of this whole big tuning business. You got all these charged particles, packets of them, huge, coming up to the surface. So you're getting a lot of tuning of these charged particles, this plasma of charged particles churning over and turning over on the surface. It's one big boiling pot going on the surface of these red dwarf stars. And when you get charged particles moving round and round, what do you get? Magnetic fields. You always get magnetism or magnetic field lines coming from any sort of electrical charge that's alternating. So you're getting a lot of magnetic activity occurring on the surface of these stars. And that has consequences too, which we'll move on and have a look at. Here we go, flare stars. As we talked about, frequent large super flares. So as we talked about, it's all convection the whole way down to the center of the star in these red dwarf stars. A lot of tuning up of charged particles at the surface, a high amount of magnetic activity on their surface. So that's in the process of these magnetic loops that form, charged particles fly through these magnetic loops. You've probably seen pictures of the sun where you get a big magnetic loop with plasma flying through it. And that's what gives rise to solar flares, where you get big bursts of charged particles. And you've probably heard about the dangers that we've got to be aware of. Charged particles at high energy, high velocity, heading to Earth are not good for our electronics, and they're not good for us either. But these babies, these red dwarf stars, because of their high surface magnetic activity, they're frequently giving off flares, and these flares are big babies. They are powerful. They're called super flares. So instead of our sort of sun spitting off the odd solar flare, these guys are giving out loads and loads and loads and loads of big ones, super flares. That's really important. And that is the reason why these red dwarfs are often nicknamed flare stars. So if you hear someone talk about, something about flare stars, that exoplanet's no good because it's going around a flare star, you immediately know what they're talking about. They're talking about these red dwarfs. And as you're going to find out as we go through, it's not all bad. It just adds to the complexity of it. Here we go. Now, here's a little bit about it. So flares Some of the positive points about these big flares is they may provide energy for the initiation of life. Life often needs electrical currents. In the models that they do, electrical currents are good to get life initiated, get those early biochemical equations going. Also, they're very good at providing energy for photosynthesis, photosynthesis being the process at which plants gather CO2 and water and generate oxygen for us to breathe and generate sugars or nutrition for animals. Very important process. We wouldn't be here if it wasn't for the plants doing photosynthesis. The plants need the energy. They get it from the sunlight. And if you're getting these big super flares with ultraviolet and X-ray radiation associated with them, that quite possibly could provide extra energy for photosynthesis. But on the counter side of that, as you're about to find out, these big, massive, frequent super flares are quite capable of stripping away the atmospheres of planets and evaporating any oceans that the planets might have gathered. Also, as you know, we're all very much aware, too much sun exposure, particularly the high energy ones like the UV light, can be very harmful and carcinogenic, causing cancers because it's harmful to genetic structure. So if you get a planet going around one of these red dwarfs, these flare stars, you know, the X-rays possibly could, as life just gets started, could the massive X-ray radiation quite happily just destroy any genetic attempt, genetic structure trying to evolve into more complex animals like cats. So now we've talked about these red dwarf stars. You've got a good idea, you've understanding of they're really abundant, they're really stable for long lengths of time, but they have got a lot of convection and stirring up of the content, so there's a lot of solar flares going on there. So let's move on a little bit to the planets, what they're called exoplanets around these. How do they find these planets, and why are they more readily discovered around red dwarf stars? Apart from the obvious, of course, there's more red dwarf stars than there are of any other sorts. Let's find out. So there are four main methods of detecting these exoplanets around other stars. There is the two big ones are called, which we're going to go into shortly, the transit method, the radial velocity method, and they're the main ones, and I'm going to talk about those a little bit more depth in a second. The other ones, of course, you can direct image them. It's not easy. And there's another process called macrolensing, and that's where you get the light of a star behind the relevant red dwarf or the star of interest and its planet. The light shot from a distant star behind it will shine through and will gravitationally lens around that star. And if there's a planet in there as well, it just gives a certain signature, very characteristic of a planet being there as that light comes around the side of the star, the front star in question. Now, you'll see here that radial velocity and the transit velocity, which we're about to talk about, are by far the commonest, in particular the transit method. Look here, this goes up to 2014, and the graph, I saw one today that went up to 2020, and it's no different to the general trend. Most exoplanets are discovered by the transit method, followed by the radial velocity method. So let's talk about these, in particular, the context of discovering these exoplanets around these red dwarf or flare stars. So yeah, transit method. This method, to do it successfully, you've got to have your star here, your big red dwarf, and as a planet moves in front of it, it starts to block out or diminish the amount of light that's coming from the star it's going around. So astronomers plot what they call a light curve. And you've got time here, and you've got degree of brightness here when you're looking at the star. And when there's no planet in front of it, all looks fine, there's the constant, you think, well, that's how bright that star is. But if there's a planet in the way and it starts moving across it, the amount of light that you're seeing starts dropping, gets dimmer, and it starts dropping like this, and you get a dip in the light curve, and it goes up here as the planet moves across, and then as the planet moves across here, of course, you're back to your normal background level of brightness. The reason why it's easier to pick up red dwarf planets around red dwarf stars here, because the stars are so much cooler. They're so much smaller. In particular, they're so much smaller in size. So the planet going in front of them is going to be taking out a larger chunk or proportion of brightness than if that same planet was going around some massive star. Say you had a star yay big, and you had a little planet going across it, and it might just dim that by about sort of 0.001%. If that was a smaller star and a planet the same size going across it, it might dim out, hey, you know, a full 1 or 2 or 3% of that light. So proportionally, the amount of dimming of a planet going in front of a smaller star is going to be greater. So this method in particular is much more effective at picking up exoplanets going around these red dwarf stars. So that's your trend. And you might think, gee, a small dip. They got pretty sophisticated equipment these days. They can detect just a subtle drop in dimness around a star, and the modern day equipment will certainly pick that up. The other method is called the radial velocity method. A little bit of background here. When you see a star and a planet go around it, or for that matter, the moon going around the Earth and the Earth going around the sun, it always looks from our view of things that, yeah, this planet is going around the star in orbit. That's not quite what's going on. What's actually going on is that both of them are going around their common center of gravity. And I've illustrated it here with this nice little GIF file. Here you'll see, here's your red dwarf, your star, your host star, and here's a planet going around it, as it looks like. But your center of gravity, the common center of gravity actually sits here. And for almost all stars, the center of gravity just happens to be somewhere inside the star. So even though, and that's why it looks like for our naked eye, it just looks like there's an orbit, the planet's going around the sun or the star and so on. But in actual fact, if you look very, very closely, the star is doing a bit of a wobble because it's going around the center of gravity. Its common center of gravity is not, as you might think, in the middle of that star. So they're both going around it, and that whole concept, physics, creates the star, if you look very, very closely, has a wobble effect like you're seeing here. So it follows from there that with a red dwarf star, the common center of gravity for that smaller star is going to be further from the star's center than if it was a much larger star. And you might think, really? If you've got a star yay big, the center of gravity between it and some tiny little planet out is going to be pretty close to the center of that star, that big mother of a star. So that big star is going to wobble a little bit, but not a heck of a lot. You get a smaller red dwarf star with that same planet off to the side, the common center of gravity is going to be further away from that center of that red dwarf star than you had in the situation with that big star, which means that red dwarf star is going to wobble around proportionately a lot more than that big massive O or B star with a planet around it. So the bottom line here, as I've read here, red dwarf star have more of a wobble when there's a planet or two or more going around them. And that's what it's all about. The radial velocity method is about detecting a wobble in a star. How? Let's find out. So this is a bit more about the radial velocity method. And the principle is that you're looking at a star and you're analyzing its spectral lines. In other words, what sort of signs that there's of certain elements that are in the atmosphere of that star. And that's a whole talk on its own, but you get these what are called spectral lines where elements sit, and they sit in their same places each time. It's called the signature of certain elements in the atmosphere of stars. And when you're looking at a star here, the star's straight in front of you, that's fine, and you see a normal spectrum. But as that star wobbles, as it goes through its phase where it's moving away from you, those wavelengths of light get stretched out or redshifted. And you'll see, so when you look at the spectrum, look at the difference between the normal spectrum and this one. See how all the lines have been shifted over to the left-hand side? And that's called redshifting. Then the star goes behind the planet. Sorry, rather the star goes in line with you, the star and the planet all in line, and you go back to your normal spectrum, and the spectral lines are in their normal position. Then the wobble of the star comes around and it's heading back more towards you again, your instruments. And the light waves here get compressed down and get what they call blue shifted or shifted to the blue side of the spectrum. So here's your normal spectrum. See how these little lines are all shifted over to the blue side? And a good illustration of this, light behaves in sound in that respect with waves. You'll notice with an ambulance, or usually with me, it's a police car after me, but you'll notice an ambulance or a police car, a siren goes, goes as it shoots past you. As the pitch of the noise, those sound waves are getting compressed as it's coming towards you. As it zooms past you, those sound waves are getting stretched outwards, and that's what you're seeing here. Here's your police car coming straight for you, and you don't know what you've done, but you're in trouble somehow. The waves, and here it's light waves, are getting compressed towards you, so you get a higher pitch if that was a sound. Light, all the spectral lines get shifted towards the blue side, shorter wavelengths. Here is the ambulance or the police car traveling away from you, a drop in the pitch, that sound. But here it's light waves going on, so the light waves are getting stretched out into longer wavelengths, which pushes all the lines out to the lower wavelength red part of the spectrum. So that method of looking for stretching or red shifting and compression or blue shifting of those spectral lines measures the radial meaning sort of coming towards or away from you. That's radial. That's off to the side, lateral. This is radial. So they're measuring the velocity or the speed at which a star is wobbling towards you or away from you. And when they detect that with the spectrometers, they can then tell you if they know the mass of the star, which they can work out. We've done all that, spectral classes, you work out their masses. You can from them work out the degree of wobble that's going on, and from there, the amount of mass of planet or planets that are causing that wobble. So that's called your radial velocity method, very important method. And as we talked about, red dwarfs have more wobble factor. So that's sort of how our red dwarf stars and how they find these planets that are going around these red dwarf stars. Let's have a bit of fun now and talk about the properties, potential properties of these planets orbiting red dwarf stars. And it does get a little bit messy, so I'm going to go through it slowly, and then I'll sort of rehash some of the main points, so you can all bring it together in your minds. Okay, these are some of the factors we're going to have to include. That you'll find out there are more small Earth-like planets around red dwarfs than there are larger stars. We'll talk about habitable zones. We'll talk about the concept of tidal locking. We're going to talk about atmospheric and climate changes that can occur in these planets that are going around red dwarf stars. We're going to talk about how planets can interact between one another. And we're going to raise that whole topic again of photosynthesis. So let's get moving. Okay. So red dwarf stars form these small, rocky, Earth-like planets much more readily than large stars. And when you stop and think about it, it makes sense. Stars form from huge, big, massive, large molecular clouds, big clouds in interstellar space of gas and dust. And then gravity gets a hold, and the whole cloud starts spinning round and round and starts contracting and shrinking down until it gets hot enough in the center and nuclear fusion kicks in and you get your star. So it makes sense if you've got a really, 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 really big, massive one, you're going to have a massive star, but also the planets. Someone once described, most stars have planets around them. And the answer was, it was beautiful. They said, try baking a cake without spilling crumbs on the bench, on the kitchen bench. The planets are just crumbs left over from the making of a star. So most stars are going to have planets around them. And those planets are the leftovers, the crumbs, the scraps from the making of that star. So if you've got a huge, massive, big, large molecular cloud that creates a massive star, those crumbs or planets that get formed are going to be larger too. So you're going to get more large gas giants around those big, large stars. Similarly, you get a small cloud of gas and dust that shrinks down to a smaller star. Those crumbs, leftovers that form into planets, are going to be smaller too. So you're going to get around these red dwarfs, there's about 3.5 times more Earth-sized planets than there are around stars about the size of our sun. It's interesting, 3.5 times more. Furthermore, 1 in 4 red dwarf star has an Earth-sized rocky planet in their habitable zone. So 1 in 4. Now you probably think, okay, what's a habitable zone? Let's move on and talk about habitable zones. That's the bottom line, is it's where liquid water is on the surface. So it's 1 in 4 red dwarf has these planets very similar to Earth in that way. So the habitable zone, is defined as the distance, or the range and distance for a planet to be orbiting a star, whereby the temperature on the surface of that planet is just right to sustain and hold liquid water on its surface. And they call that the habitable zone. So it makes sense from there that if you've got a large A star, like OB or A star, a large hot star, it's going to make sense that temperature zone to be right is going to be further out, a lot for a larger distance from the star, because anything inside there is going to be too hot, it'll evaporate. Anything outside, of course, it's too cold and it turns to ice. Here's the sun here, and that's the habitable zone here, and Earth is in the sort of pretty close to the middle of that habitable zone. It's called 1 astronomical unit, which is about 150 million kilometers. And inside of there, you're starting to get into the orbits of Mercury and Venus. It's too hot for surface liquid water. You get further out into Jupiter and Saturn, and it's too cold, so you get ice. You just don't have liquid surface water. Someone asked me once, how many of the stars in our solar system are in the habitable zone? The answer is 2. Mars is in the habitable zone. And you might think, well, hey guys, if that's pretty, that's okay, it's great to hear. Where's all the liquid water? You're going to find out shortly why the liquid water is not there on the surface, but it is in the habitable zone. Then you get down to these red dwarfs like the K and M spectral class stars. And as you suspected, yep, you're right. The habitable zone, the temperature where it's not too hot, not too cold, often called the Goldilocks zone. You might hear that, the media uses that term. It's no different, it's the habitable zone. And that's the temperature, it's just right for liquid water to be on the surface of that exoplanet. And yet it's a lot closer in to the star, to these cool stars, because these red dwarf stars, remember, they're small, they're really cool, and they're really dim. So your habitable zone is a lot closer. That has consequences. Let's go and find out. The other little thing I will mention in here too is not only do the zones get closer in, the smaller the star, you red dwarfs, not only does the zone get smaller, the zone gets narrower and narrower and narrower. So the planets that are in that habitable zone tend to be more packed and closer together, which then has consequences whereby you start getting influences, gravitational and atmospheric influences going on. So that's also very relevant. So that's the point of the slide, was just illustrating as these temperatures get down to these sort of cool, these very, very numerous, cool, dim, small red dwarf spectral class K and M stars, the habitable zone's getting closer and closer to them, and that band is getting narrower and narrower and narrower. So yeah, as I alluded to, this has consequences, and the big one is you get 2 or 3 planets, they start interacting with one another, but also there's the key factor is, even if you haven't got that, the fact is all these planets are really close to these stars, and you start getting a gravitational or a tidal, what they call a tidal locking effect. You might think, really, what's gravitational tidal locking? What's that? Is that some new dance that we've got to do on the beach this summer, or what? What's tidal locking? We'll talk about tidal locking. Synchronous rotation. What's that? Is that some new washing machine cycle? The new Fisher and Paykel washing machine, it's a new cycle, synchronous rotation. No, it's not. We'll explain about that shortly. And I'm going to show you how it affects the magnetosphere. That's the sort of magnetic lines that go around a planet that protects it. We'll talk about how that affects its atmosphere and climate. So let's move on. Let's rock and roll. Okay. So tidal locking and synchronous rotation. The principle here, if you get a body that's orbiting another body, and the mass of those bodies are in proportion such that, and they're orbiting reasonably close, the tidal interactions between those two bodies will be fairly strong, such that you get a bulge, a tidal bulge around the smaller object that appears. Remember, it's not, they're orbiting around the common center of gravity, but let's keep it simple for these purposes. This smaller object, such as in here, we've used the moon going around the Earth because it's a lovely example, because this is what you actually see in life. Goes around, it creates this tidal bulge, if you will. And by the way, the bulge occurs on Earth as well, and that's the cause of the seaward tides. That's what causes them. It's the bulge on the Earth. So you get this bulge, and that bulge itself, the two bulges between the Earth and the moon, they gravitationally attract one another. And essentially the outcome is it slows the rotational rate of that smaller object going around the larger one, whereby if you give it long enough, eventually it settles in a stable state called synchronous rotation, whereby the same side of that smaller object always faces the large one. And that's what we see with the moon. That's when you look at the moon, it's always the same side is facing us, because as it goes around, the actual moon is spinning around at the slow rate. It does one complete turn on its own axis for every orbit around the Earth. Now, if you get that with a planet going around one of these red dwarf stars, it's got to be in the habitable zone, because that's all we're interested in, because we want surface liquid water. And it's got to be close up, because that habitable zone's got to be close. So to get that close, most of these planets are going to fall into a state of synchronous rotation, where one side will always be facing the red dwarf star and one face will always be facing away. And you're immediately thinking, yeah, I can see what's going on here. You're going to have one scorching side constantly facing your sun, your star, and one side constantly facing out to space. That's always going to be cold. And you've got to question, you've got to question, hey, how viable is that for life? And you're right, that doesn't sound very viable, but there's a little bit more to the equation than that. It's not that simple, but that is a hurdle that a planet's got to overcome to support life and for cats to evolve. Now, I want to move on. I mentioned earlier on that this whole tidal locking thing is also relevant for a very important concept called a magnetosphere. Yeah, and a magnetosphere, here it is with the Earth, a magnetosphere refers to the fact that there's a good planet, good for life, as you'll have this, as the planet spins around Earth, it's got molten iron, and iron conducts charged particles, electricity, and that molten iron is going round and round as the Earth spins on its axis every 24 hours. What do you get? We've already spoken about it. What do you get when you get tuning, rotating, charged particles or conductive metals going round and round? You get magnetism, you get magnetic field lines. And Earth has got this molten core going round as the Earth rotates, and you get sort of, it's like a magnet. You've got your North Pole here, your magnetic field lines go right round and back into the south side, the south magnetic pole of the Earth. And this is called a magnetosphere. It's a global coverage of the whole planet, in this case planet Earth, of magnetic field lines. And the importance of that is if you get any nasty, as I've done on this little diagram here, you get these solar flares that we get from the sun, and think here, multiple frequent super flares from these red dwarf flare stars, they start heading towards you, and they potentially can be serious and harmful to life, as we spoke about. Remember, we talked about genetic damage and so on that it can cause. So it's not necessarily a good thing. It can be very harmful for life. And look, here's Earth with one of these the global magnetosphere, and it deflects these charged particles away. Pretty much like I do when I see a Brussels sprouts heading for my dinner plate, or maybe one of Josh's duckweeds heading for my dinner plate. I'm going to deflect that away. I'm not too keen on that, thank you very much. So that's what these magnetospheres are doing. They're deflecting away charged particles, potentially harmful, high-energy charged particles coming from these solar or sun star flares. It's deflecting them away. So you can see the point. Global magnetosphere is a good thing. And if you don't think it's a good thing in terms of the an atmosphere, we spoke about Mars earlier on. Mars is in the habitable zone, but why doesn't it have liquid water? The reason being is the atmospheric pressure, which you need a decent pressure to support a liquid on your surface. The atmospheric pressure on Mars is less than 1% of the atmospheric pressure on Earth. Why? Mars was very small, so it cooled down. Its core, its molten iron core solidified, so it lost that ability to have an electrically conducting molten iron core going round and round as it rotates. So what happened? It lost its global magnetosphere. What happened then? The charged particles just had to have a free run. What do? They strip away your planet's atmosphere, as we alluded to earlier on a few slides ago. So that's what happened to Mars. So that's a good lesson on if you don't have a global magnetosphere, you're at risk of losing your atmosphere, which drops your atmospheric pressure, which means that even though you are in the habitable zone, you don't have the atmospheric pressure to support that liquid water. So what has that got to do with tidal locking? Well, with the Earth, as you know, it spins completely every 24 hours, and that gives the molten core to spin round and round. Tidal locking, remember, I said that it slows your rotation rate right down. So you only rotate on your axis once every time you orbit your host star. And that, if it's too slow, will most likely be inefficient for the rotation rate to be sufficient of that molten iron core that you hopefully have in the middle of your planet. It's not rotating and it's not churning enough to create magnetic field lines going around your entire planet to protect it. So you end up with a weak, if any, global magnetosphere if you're tidally locked. And it all depends on how slow that synchrotron radiation occurs. Synchrotron, getting mixed up here, synchronous radiation, I really am getting mixed up. Synchronous rotation, there's a thing called synchronous radiation, which I often talk about. So synchronous rotation, the spin rate at which you're going around, if that spin rate is really, really slow, you may not get a global magnetosphere. If, however, you are a little bit further out, you might be okay. But you can see that's another hurdle you've got to get over. If you're going to be a planet around one of these stars, you've got to be in close to be in the habitable zone, but you may not have a global magnetosphere, in which case you're in trouble, mate. The other thing about tidal locking, so I've mentioned that it affects your synchronous rotation, and that's bad news. Hot and cold, hot one side, cold the other side. Life doesn't like that. You might not have a global magnetosphere. But there are possible things that can occur that might be actually okay with a tidally locked planet. And that is, if you have a thick enough atmosphere on your planet, it just might be okay. Atmospheres are good at transporting heat around. And you might be able to transfer, it's quite, computer models show it is very, very feasible for that hot scorching side with a thick atmosphere, heats that atmosphere up, and it actually rotates around the star and delivers that heat to the cold side facing outwards from the star. And that transport of heat might actually create a moderate climate after all. So that has been shown in climate models. So it's not all doom and gloom. The other thing is, if you're lucky enough to on that planet and you've got a reasonably good atmosphere, you're rotating at a rate whereby that internal core of iron is spinning around, it's giving you a global magnetosphere, you are tidally locked, synchronous rotation, you have a thick enough atmosphere that's maintaining there because you've got your magnetosphere, and you're starting to form some oceans, some liquid water. Because why? Because you're in the habitable zone. What happens with oceans that heat up on that dayward side? You get clouds, you start getting a bit of evaporation. And if you get enough clouds, what do clouds do? They reflect light, the white. So if you get enough clouds that reflect light on the day side back out, that may lower the temperature enough and buffer against what they call the greenhouse effect. The greenhouse effect is where you heat up water and methane and carbon dioxide, they retain heat. So the temperature of the planet gets higher and higher and higher, which means more and more water evaporates, so you get more water vapor in the atmosphere, and it just goes on and on and on. That's actually what happened to Venus. That's why Venus is dry as a chip as it is now. It's because it got too hot. Its oceans evaporated. Water vapor loves driving the temperature up even higher, which any more liquid you got left over evaporates even further and further still. So if you've got an atmosphere that's distributing the heat, you have reflective clouds above that. They will deflect a lot of that heat from the star, so it's not so hot, and that in itself will protect your oceans. So it's still possible to have a nice moderate global climate and liquid water in one of these situations, one of these planets in a habitable zone around these cool dwarf stars. Now, so that's talks about the gravitational effects of the fact that the planet has to be so close to its host star. I also mentioned to you that because it's come from a smaller gas cloud, the star, it's got lots of smaller little crumbs left over to create these smaller rocky planets. There's more of them. And the planets tend to be more closely grouped. So it also follows from there, you're going to get gravitational interactions between these planets, which also makes things complicated. It can increase, and I'm about to show you, the eccentricity of the orbit. That's how elongated, as opposed to circular. When something increases eccentricity, it means it gets really long and oval-like. It may increase the axial tilt of a planet. So instead of being upright, it tilts over. Also, all the above forces can heat up and cause tectonic plates moving and volcanic activity on the planet as well. So let's explore this a bit further rather. So yeah, here's an orbit, and this can certainly happen quite happily in models, dynamic models of planets going around stars. After a while, they all start interacting with one another, and they end up not doing a circular loop like that. You can get stars really highly elongated or eccentric orbits, whereby a planet will go right close around a star and then head way, way, way out here and zoom back in. And it follows from there, you're going to get extreme seasons and extreme climate changes. It's going to be really, really hot around here, and it's going to be much colder out here. Life does not like change. It likes stability, for it to gain hold and for it to last long enough to evolve and develop into more complex life. So that's not a good thing. Yep, and the dynamic models of planetary motion definitely shows you get 2 or 3 or more planets, close proximity to other, they start creating eccentricity or elongated orbits. The other thing is, as I said, the axial tilt. Earth has an axial tilt of about 23.5 degrees, and that's what gives us our seasons, our summer, autumn, winter, and spring, and so on. And it follows that if the axial tilt, because it's getting gravitational influence, not only gets more and more marked, but also maybe changes, swings around, and so on, you're going to get more extreme seasons going on, and it follows from their climates. And once again, that is not good for life. Life to get started and to evolve and get more complex, it likes uniform. It likes a uniform, constant environment. It does not like change. And one of the reasons we're actually lucky that we're roughly about 23.5 degrees on Earth, and that is kept stable. We don't have a big wobble of the axis on Earth. Why? Because we have a relatively large sized moon next to us that keeps our axial tilt stable. We take that for granted. But these planets there, if they're interacting with one another, they can get huge elongated orbits, and their axes can go from extremes all over the place. And that creates a lot of sort of fluctuating extreme seasons and climates. Life does not like that. Now, there is a potential counter to this, however, that may play into the hands of life in the situation, is that red dwarfs, remember we mentioned the cooler, you may be aware that as things get cooler, they emit more low energy, longer wavelength infrared radiation. And infrared radiation gets absorbed really, really readily by water and carbon dioxide vapor in an atmosphere. So even though you might be having some of these crazy orbits and just, or let's call them suboptimal orbits and axial tilts going on, because of your interactions with your close host star and also your other close planets that are close to you, that, yeah, you've got an atmosphere going on there. You've got a lot of infrared radiation pouring out of this red dwarf, cool, dim, small red dwarf star. It's pouring a lot of infrared radiation. That might play into your hands, and that in itself will start to get absorbed by your water vapor and your carbon dioxide gas in your atmosphere, and that offers a more stability and allows you to have a more moderate climate. And yeah, and also I mentioned that, I've written it down here, your methane gas also. These are your probably your hothouse gas. You've probably seen these gases, water vapor, carbon dioxide, and methane gases used in the context of Earth being a greenhouse gas and causing heat up. And it's these gases in an atmosphere of one of these planets going around with a lot of infrared radiation that plays into their hand. So that's a potential counter. So it's not all lost. Yeah, and the other thing is you get these stars that are these long elongated orbits that are causing these extreme climates and stuff. But here's another positive thing. As you approach the star, like here's the orbit. I don't know what you guys can see, but mine's a bit blocked off by our pictures. But anyway, you can see these long elongated orbits here. As it approaches around the host star, the tidal forces can be so great that you get a stretching and pulling and moving around of all the internal plate. There are plates in there, but your material, your mantle starts moving around and gets molded like plasticine and stuff. And that generates heat inside the planet. And a good analogy of that, you get a paper clip and start wriggling it backwards and forwards, bending it. What happens to the middle? It gets hot, doesn't it? You go and put your fingers on it, it gets warm. Same principle. You start flexing and molding the internal goings on material inside a planet, it's going to heat up. And that can create geological activities, maybe tectonic plates, volcanism, volcanic activity. And what those processes do, allow a planet to recycle a lot of materials, in particular carbon. Carbon is important that it doesn't get trapped underground. It gets recycled back up again. It's important for life and so on. It's important gas in the atmosphere to keep those climates moderate. So if you do get elongated orbit, you might be lucky enough to get geological activity that allows sort of volcanic and geological processes going on, which then is sufficient to allow life to actually get started and to evolve further. The infrared radiation, it's high in it. You've got to question yourself, is that going to be sufficient for photosynthesis? Because remember, plants and life, they love our sunlight, and our sunlight is predominantly in visible wavelengths, which is a lot stronger energetic wavelengths than your infrared that's coming out of these red dwarfs. So you've got to say to yourself, well, is the infrared, this low energy light from these cool dim stars, is it going to be sufficient for photosynthesis? We don't know. If it isn't, possibly the higher X-ray radiation, the higher energy X-ray radiation that tends to be associated with the high energy particles in the solar flares coming towards you may well counter that. So there's every chance that photosynthesis from plants, if plants can take hold in these planets under these moderate conditions with water, and you may well get photosynthesis occurring. And photosynthesis, as I mentioned, creates oxygen, which is good for aerobic metabolism, which animals use. We breathe oxygen and breathe out carbon dioxide. But also it creates that protective O3, that ozone layer of 3 molecules of oxygen together, which then protects that planet and that life against these harmful high energy radiation photons that can do harmful damage to the genetic makeup of these life forms that are trying to get started. So you can see that there's a lot of factors, a lot of negative factors going on, but there's a lot of other things that can go on that can counter them. So yeah, there's every chance life may form. I put here about people, sort of how evolution of your eyes. The reason that we optimally see invisible wavelengths is not a coincidence. Animals evolved to see things in visible light form, because that's the predominant light form for our sun. Animals that that developed eyes that were better in infrared, for example, didn't prosper so well, or the more nocturnal. But it would be easy enough for a complex animal to quite happily, their eyes would adapt and they would see quite happily in the infrared wavelength. So that's not a problem. That's why I just wrote that little bit down there. So I know that's been a lot to take on. I've rambled on a bit, but let's just briefly summarize and bring it together. So you've got these red dwarf stars, which make up 70%. So there's loads of them out there. They're cool, they're small, they live long, stable lives. The planets, there's more chance of finding an Earth-like rocky planet in the habitable zone with liquid water on its surface. But because it has to be so close, you've got the risk of tidal locking, which can create that state of synchronous rotation, which leads to extreme hot side facing the star and the cold side facing away. It can also cause a reduced magnetosphere because you're not getting the rotation, the tuning around, and that can cause the atmosphere to be stripped away. But that can be countered by, if you get a thick atmosphere going on and a thick ocean going on, that can counter that quite happily, potentially. You get many close planets. You tend to get planets that are more closely together in these orbits, in these habitable zones, which they interact, and it increases the elongatity, the sort of elongatedness or eccentricity of these orbit or its axial tilt, which causes extreme seasons and climate change, but in particular an unstable climate, which life doesn't like. But that can get countered by infrared radiation, which loves to get absorbed by water vapor and carbon dioxide and methane in the atmosphere, which can create a bit of a heat trap, which can, and if you get an atmosphere to spread that heat around the planet, then that can also help in creating a moderate climate, which life likes. And the other thing that's important to life is that whole process of getting plants on a planet, getting some photosynthesis underway. Is infrared radiation enough? We don't know. Models are working on it. But if it is, X-rays may make up for that, or they may potentially do harm. That's sort of, you have a few factors to weigh up there. So that's red dwarf exoplanets in a nutshell. So the future, where are we in understanding these worlds? The bottom line is, it's in its infancy. It's pretty exciting stuff, isn't it? But it's in its infancy. I'm going to show you briefly the next generation of large ground-based telescopes. The space-based telescope, the latest one up there called TESS, I'll show you, and the James Webb Space Telescope that hopefully will be launched next year sometime. So currently our best telescopes on the ground are like Keck, the likes of Keck, were about sort of 10-meter diameter telescopes. The bigger a telescope is, its diameter is the most important factor. And that enables you to capture more light and analyze anything you're looking at in better depth. The next generation of ground-based telescopes that are now being built are going to be between 30 and 40-meter diameters. Wow, that's just going to blow these current ones away. Going to get much better definition. And in particular, the main one that's being built at the moment is called the Extremely Large Telescope, a 39-meter diameter telescope built by the Europeans in the Atacama Desert in Chile. And it's going to be able to look in the optical wavelengths and the near infrared. It is planned that it's going to see new light about 2025, so about 5 years' time. So that's really going to be exciting. It's going to have much better looks. It's going to be able to detect more of these red dwarf stars and their surrounding planets, and it's going to be analysing them much better. You've all probably heard of Kepler, that did a lot of work detecting these planets. The current one that got launched 2 years ago is called TESS, or the Transiting Exoplanet Survey Satellite. This was launched by NASA Space Telescope above the atmosphere, so it's better at looking at these sort of cool, dim, infrared emitting red dwarfs rather, and their planets. And it does a complete survey of the sky every 2 years. Kepler's role was just to show whether exoplanets were out there, and it just focused all that time on one little segment of sky. TESS is different. We now know from Kepler that exoplanets are out there big time. They're hugely abundant. And TESS now is just doing complete surveys of the sky of all that, searching for nearby red dwarf stars and searching for the exoplanets. That's the main target. So it's already done a complete survey. It's been in space for 2 years already, but the future holds a lot for that. It's going to bring in a lot more data. And the other one, of course, is the James Webb Telescope. That's going to be that's a space telescope, hopefully launched next year, but it's huge diameter, you could see there. And that is not only going to be able to detect red dwarf stars much, much better, and their planets, that will be capable, if all goes to plan, of actually analysing the atmosphere of these exoplanets, looking for what we call biosignatures. In other words, chemical signs, spectral signs of chemicals in the atmosphere that tell you that there's life going on somewhere on that planet. Oxygen is your classic example. There's lots of, if you look at Earth's atmosphere from away, if someone else was looking at Earth's atmosphere, there'd be loads of fingerprints in that atmosphere, of our atmosphere saying, hey guys, there's life here. So, just wrapping it up, living under a red dwarf star, my 3 main messages were they're abundant. The most abundant, 70% of all the stars in our Milky Way are red dwarfs. Can't see them with our naked eye because they're so dim. They live extremely long lives, up to 56 billion years on that stable main sequence part of their life program. However, they're very hyperactive, a lot of surface magnetic activity going on because they're tuning charged particles, all that convection that creates these frequent high energy super flares. So those are your 3 messages. Planetary conditions, it's complicated. There's a lot of factors going against them harboring life, but there's a lot of factors that may come into play to counter those and actually make it quite favorable for life. So, but I always like to give homework. So tomorrow night, debate with your family or friends, have a debate with them. Where exoplanets around Proxima Centauri, remember that was one of the star systems, they found an exoplanet, it's a red dwarf, and it's our closest star system. Whether or not Proxima Centauri, the planet around it, the exoplanets, is favourable for life or not. Have a discussion, debate it. Don't involve alcohol though, it might get a bit scrappy. Next week, while you're looking for new friends, because you've lost all your friends this week, I suggest you go onto the social media site, whether it be Instagram or Facebook, and look up the TESS social media site and follow its progress in identifying new planets that it's finding around red dwarf stars, because it's just starting to scratch the surface. That's going to be really, really exciting stuff in the coming years. So friend it now and see what's going on there. So that's your homework. So that really is living under a red dwarf star, favourable for life or not. I thank you for your attention time. I hope I didn't prattle on too much, but let's move on to question time. James, any questions out there? Hope they're not too hard.
Yeah, there's a couple of them.
Okay.
So one from Ben, he was saying, can you see red dwarf stars with like a 8-inch or 10-inch Dobsonian? And if so, what colour would they appear?
Yeah, good question, Ben. With difficulty, I think you'd need a bit bigger than that. Possibly maybe at the brighter end of the spectrum. My understanding is you pretty much need a professional telescope. Definitely not with the naked eye. You mentioned a 10-inch. Maybe that would be worthwhile looking up. If you were, you'd be struggling. It's probably may well be possible, but you'd be struggling, Ben. And what colour would they be? Yeah, they're going to be cool. They're low temperatures, so they're a red colour because of their surface. So they're going to be very, very dim. If you manage to spot one, good luck to you there. But they're going to have a very glowing, like an ember. You know, an ember in the bottom of your fire at the end of the night. It's going to be a sort of a ruddy red complexion to it.
So that's going to be
much like your Betelgeuse. Betelgeuse has a surface temperature of about 3,500 degrees, not because it's a red dwarf, but because it's actually a red supergiant. But because for totally different reasons. But my point being is that has a surface temperature of 3,500 degrees, just like these red dwarfs. Different stage there of evolution, so don't get that mixed up. But my point being, it would look the same color as Betelgeuse in the sky.
Yeah, one of my questions was, how would you differentiate between a red giant and a red dwarf if you just seeing a
It comes down to your luminosity. Remember that Hirschsprung-Russell diagram? Actually, let's go back through that, shall we? Which you never escape in any of my talkings. You're always going to get hammered with this diagram. So there it is. You're plotting here. You're plotting your spectral classes, and here's your luminosity, and here's your red dwarfs here, low luminosity. Your red giants and supergiants, really, really bright. These are actually stars, these big, massive stars that have moved off and become massive red giants really early on in their stage. And that's how you see. Yeah, so good question there, James. They're exactly the same color, but they're a lot brighter. So you're going to see them. You see them with your naked eye, like case in point, Betelgeuse. There it is up here. You see it, so it's going to be brighter. And as opposed to red dwarfs, you can't see with your naked eye. And the reason being is luminosity is a function. One of the main functions of luminosity is the size of something. The bigger something is, it is naturally really, really brighter. So it follows that these stars are very, very small, so they're very dim. So you'd plot it. You'd see the color. Aha! You'd measure how bright it is. You'd plot that on your Hirschsprung-Russell diagram, which you should have handy at any time, and you'd see where it was sitting on here, and that would tell you what sort of star it was, what part of it's in its evolutionary stage.
So another question from John was saying, does that mean that having an Earth-sized planet around a star the size of the Sun, is that quite a rare occurrence?
A Earth-sized planet around the star, in other words, the scenario that we've got now, our solar system. Yeah, there certainly are, it depends how you look at it, there are certainly far, far less G-class, which is our Sun is, it's a G spectral class. There are far, 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 far less of those than red dwarfs. Red dwarfs tend to give rise to smaller planets. So I'm sure any combination, it's out there, but they're going to come less frequent. Because remember, I think the figure was it 3.5? I think I sort of said in here, a red dwarf is 3.5 more times likely to have a Earth-like rocky planet around it than our Sun, a G-class star. So it's 3.5 times more likely for a red dwarf, just on a one-to-one basis. You get one of our stars here, our Sun, G-class, and a red dwarf. This one red dwarf, is 3.5 times more likely to have an Earth rocky planet around us, and that's on a one-to-one basis. And then these red dwarfs, there are so exponentially many more of these red dwarfs than there are these G-class suns. So they're going to be out there just by sheer sense of just numbers. Is what they estimate, what about 200 or 300 billion stars in our galaxy. So I don't doubt for a minute that little combination out there is going to be out there of another, our Sun, it's a G25 spectral class star. That's going to be out there, and it's going to have another Earth like there. Absolutely, most likely. But it's going to be far, 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 far outnumbered by another rocky planet around a red dwarf.
Okay, that's well answered that. Barla's got a question as well. He says, is it the assumption that all life in the universe is based on being water reliant?
Yeah. Water is such, absolutely, for two reasons. One is water is such a lovely solvent. There's no other solvent. People sometimes talk about ammonia possibly as a second, but Jesus, or Jeepers, that's a really far away second. Water is a far better neutral solvent for chemicals. The other thing in there is the commonest things occur commonly. What are the hydrogen? What is oxygen? What is water made of? Hydrogen and oxygen. Hydrogen is the most abundant by a country mile of all the elements, and the third most common element is oxygen. So water is made up of the first and third most common, and the second one being is helium, which is non-reactive, it's inert. So let's say water is made up of the top most abundant two reactive elements in the universe. So water is going to be more abundant than anything else by far. It is a nice neutral pH neutral thing. It's not damaging for cells and so on. It has lovely properties in it where, because of its bipolar sort of makeup, the shape of its molecule, it has properties where it can form ice and so on. Ice forms a lovely layer at certain temperatures and allows the liquid water underneath it, which can keep liquid water on a planet even when it's going through a freezing state in its evolution. Water is just everything. And the other thing, Bali, which you've raised an interesting thing, is people often say, oh, you say that carbon-based life, most life's going to be carbon-based. Absolutely. Carbon is the next most commonest element in the universe. Your commonest is hydrogen, reactive. Your second one is helium. Hydrogen and helium make up 90% of all the elements in the universe. Helium, forget about it. It's inert, doesn't react. So let's go. The next one is oxygen. The next one is carbon. Oxygen, carbon is a country mile ahead of all the other guys behind it. So once again, the commonest things occur commonly. Carbon is more common. Carbon is so versatile and linking in with so many other bigger molecules. Then you might say, but silicon is the same line in their periodic table. It's very similar and versatile too. But silicon has got an extra layer of probability orbits of electrons around it. So the bonds are weaker. So the carbon bonds are more versatile and they're a lot stronger. Carbon is more far more abundant than silicon. And the other thing is water, as I've just explained, is your best solvent, and you need a solvent for chemical reactions. What do you get when you put carbon with water? You get dissolvable gases, don't you? Carbon monoxide, carbon dioxide, which are soluble gases. What do you get when you bring silicon with oxygen? You get sand and brick. You get solids. And I think Dr. Spock in one of the Star Trek things was told there was some rare silicon life form on a planet, and they were getting crook, and they wanted Spock to go down there. And he says, I'm a doctor, not a bricklayer. So, it's going to be life out there. It's going to be carbon-based, and it's going to be reliant on water. Good old-fashioned H2O. Cheers to water.
So Ben's got another question. He's saying, if red dwarfs have smaller planets that are closer to the star, it seems that the planets would have closer orbits relative to each other, and then will they have to have transient gravitational effects as they pass each other?
Yes. Yeah, absolutely, Ben, absolutely. And that's I was talking about here, the interaction. So the planets, they will be close to the star, so there's gravitational effects, and your big one is your tidal locking. Then your next big one is because you've got these multiple rocky planets, because they just naturally form from that smaller molecular cloud, and they're going to be closer together to all be, if you want them in that habitable zone, they've got to, because remember I said that habitable zone is not only closer, but it's narrower. So if you're interested in planets in that habitable zone, you may get a few of them together, and they are going to interact, and and that's what tends to happen with your planetary dynamic computer models will show that they all start interacting, and given time they'll break away from circular orbits and you'll start getting long elongated orbits. So there is your sun here, and if you got a long elongated orbit, it goes right around, that zips around, a planet zips around it, and yeah, absolutely. So it tends to cause orbits that are really elongated, elliptical orbits. That creates unstable climates and seasons. They also, as I mentioned, that dynamic gravitational interaction between planets creates more of a wobble in the axial tilt, which creates extreme seasons and changing seasons, unstable climates. Yep, and that life does not like that. But as I mentioned, it can be moderated because of those red dwarf stars are giving out lots of infrared radiation, which water vapor loves to trap, and that tends to moderate the climate. So good point, Ben. Yep, that does happen. It's a negative point, but it can be countered by the conditions of the red dwarf star. Does that answer the question to that?
Yeah, sounds good to me. He's got another 2-point question. He says,
oh my goodness, Ben.
He says, your library is very impressive behind you. He wants to know, what is the percentage of non-fiction versus fiction books? That's the part one of the question. And part two of the question is, what is your favorite astronomy book on your bookshelf?
Yeah, okay, good. Mostly it's all non-fiction. I don't think I actually own any fiction, actually. Gosh, no, it's all non-fiction, Ben. And looking around me, it's mainly all science and astronomy, a little bit of history. I like particularly war, not because I don't like war, but I just think it's important that we remember what went on, and out of respect. Bit of geology, and otherwise a little bit of chess. I've got a row of books on chess, and I've got 3 rows of books on Elton John. I'm an Elton John nutter. There you go. I've been exposed. So, and what was the second question? Was favorite? Yeah, I've actually I've got a handful, and I've actually propped my laptop up at the moment on some books, and they're actually sitting on my favorite books. They're just general astronomy books. And one that I'm reading at the moment this is a really good one. This is actually very relevant to what we've talked about. And it's because they've just retired the Spitzer telescope, which was a space telescope dedicated to infrared wavelengths, which of course we know is really important for looking at red dwarf stars and their planets. And this book is all dedicated towards studying your Spitzer's and infrared wavelengths. I love physical books, and I love the smell of books. You can't beat it, can you? So this is new, this book. So that's sitting on top of my list to read. So I hope that answered your question. I'm a space nutter, a chess nutter, and an Elton John nutter.
Oh, there we go. I hope that answered your question.
And that's me.
Yeah. Well, thank you all for attending. Thank you very much, Chris, for doing the talk. As usual, mind-blowing. Very, very fascinating. As I've always liked Red Dwarfs. And as John said, he got to season 4 of Red Dwarf, and that's when he stopped watching. So... thank you all for attending, and we will be in contact on the Facebook page and in the from email about what's happening with the next few meetings. At this stage, it's almost certain we'll be on here for the next meeting, which is.
And I'll just show in there, guys. Be safe. Importantly, be kind to one another. No matter what planet you live on, be kind to one another and have lots of fun. Take care of one another. Be safe.
Bye, everyone.
See yous.